Hey y'all, I'm Mr. Boyden and you're you, so we might as well be learning about describing location in a distribution. Here we go. To start today's video, I want to first review something that we talked about in the previous video with shapes of graphs. So think about this. 2 years ago, the mean AP calculus scores in my class was a 3.6 out of 5, and the median was 5. What does that tell you about the distribution or the shape of the distribution of my AP Calculus scores? Pause the video if you want to think about that and try to figure it out. What this tells us, because the mean is less than the median, that's an indication that there is a left skew in the data. And actually, since it's out of 5, this tells us that at least half my scores, or more than half the scores, were 5s, which was really awesome. That was a really good class. So the distribution looked something like this, okay, with a lot of 5s, a few 4s, there were a couple 1s or 2s down here. So that's what that was. Here's another one, so let's try it again. According to Vanguard's How America Saves 2019 report, published this month, the average American worker has about $192,877 in their 401k account and a median balance of $58,035. Wow, a situation where the average is triple the median? Holy moly. That tells us that there is a serious right skew. So I want to remind you that because the mean is less resistant, if there's skewness, the mean is going to be pulled toward that skewness more than the median. So that's why it's to the right. So this suggests to us that there's, wow, if the average is that big, there's some people that have a lot more money than that in their account, even though only half of all people have more than 58,000. So that's review. Let's get to the new stuff. Today's video, we're going to be focused on 4 things: percentiles, cumulative frequency graphs and cumulative relative frequency graphs, z-scores, and how transformations of data change the shape, center, and variability of those distributions. A percentile of any given value or data point in any data set is just describing the percentage of the data or the values that are below that point or that are less than. There's a little bit of debate. In some textbooks, it'll say that are less than or equal to, and that's why I've kind of bolded that less than to remind me to say that. But in large data sets, it turns out to not really matter. So in any event, enough talk about that. Let's try an example so you can see what I'm talking about. So down here, we have the tiny little quiz scores from one of my pre-calculus classes, and a perfect score was 8. So let's consider if you scored a 2, what is your percentile? Well, what we would do is we would count up the values that are less than that value. So draw the line. How many data points are below? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values. So 11 out of the 29, and you don't need to count them. I gave it over here. And when I do that, what does that come out to? That's 0.379. So that's 0.379. Now, typically we want to give our percentiles as a whole number. And I know that 0.379 would round to 38%, but I'm going to write 37%. Why is that? It's because if I rounded this to 38, I would be saying that a person who got a 2 beat 38% of the class. And that's not true. They're not ahead of 38% of the class. They're ahead of 37% of the class, and technically just a little more, but they're not quite to 38, so that would be misleading. That's the 37th percentile. Let's try another one. Let's try if you scored a 4. So if you scored a 4, how many people did you beat? Well, counting from the left, we're already at, this is the 11th person. So 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. You beat 21 out of the 29 people. So 21 divided by 29 is 72.4. And so I'm going to say that that implies, and I'm going to round it down, that is the 72nd percentile. And you know what? It dawns on me, I should not write 37%. I should say 37th percentile. Okay, now the last one is a little tricky. And this is where that definition up here gets a little funky. And you know what? If I'm not your teacher, if you're at another school or whatever, or if you have a professor later in your studies that says it a different way, then that's totally fine. Go with them. but I'm going to go with this definition. So if you scored 8 points on the quiz, you might think, oh, I'm the top one. I'm 100%. You're not. Because if this definition is less than, you didn't beat yourself. You beat 28 out of the 29 people. And what percent is that? That is 0.9655. That is the 96th percentile. Whoops, 6th. So I kind of have this concept question down here. Like, what does it mean to be 100th percentile? It really depends on which definition for percentile you use. The one I have up here is less than. So if that's the definition, to be 100th percentile, it means that you got a higher score on whatever it is than everybody else. But that would include yourself. You can't get a higher score than yourself, so that's not possible. So generally speaking, we don't really see the 100th percentile or talk about it because you'd have to be a number that's bigger than any number in the data set, which would mean you're not in the data set. So just kind of a weird question. Where are percentiles used? Percentiles, you've probably seen them used, like if you went to the doctor when you were a kid, they typically will chart the percentile of your height and weight for your age. So my experience, I'm kind of a bigger guy and I kind of always have been. I've always been in those higher percentiles or whatever. Another place for percentiles is often on if they give like an IQ test potentially or an aptitude test. Rather than giving the raw score, sometimes if it's like a standardized exam, they'll give you your percentile score. Like for example, the PSAT does this. They'll send you your percentile. So when you get back the score, it's always interesting going through those with students because sometimes they'll say like, hey, Mr. Boyden, I got the 22nd percentile. Isn't that really good? No, that's not good. That means you only beat 22% of the people that took this test. It means you're one of the lower performers. Conversely, if someone says, hey, I got 97th percentile, is that good? Yeah, that means you're in the top 3%. That's phenomenal. That's really good. So those are common places we see it. It's just a really quick, easy way of describing it or describing the location in a distribution rather than having to understand what all the raw numbers mean. So let's keep going. Let's talk about cumulative frequency graphs and also cumulative relative frequency graph. And I want to remind you that relative frequency is very similar, basically the same idea as a proportion or a percentage. Okay, and we saw previously that all of our relative frequencies have to add up to 1 or 100%. So let's take a look at this graph. This is a graph that was created based on some data set. And down at the bottom, we have time. On the left, we have the cumulative frequency, and we're talking about the amount of time spent on homework in this graph. Here's how to read it. So for example, if I come down here to 40, if I trace up to find this point, and I trace it to the left, the way to interpret this is that, since it's a cumulative frequency, it says 10 people spent 40 minutes or less on their homework. Let's do another one. What if I want to know how many students spent more or less than an hour? Let's go up from here. I'm going to count over, and maybe I missed. I think I'm pretty close though. It looks to me like that lands at 19. So that tells me that 19 students spent 1 hour or less on their homework. That's what that data point there is indicating. And you can do that. You can trace down and left from any of these data points. Up here it ends, and if I trace over, that hits at 50. That tells me that there were 50 data points in this data set. There were 50 students who were asked. And then this goes down and it hits, and I've done a curvy line there, but I believe it hits at 120 if you really trace it carefully. And what that indicates is the person who spent the most time on their homework spent 120 minutes on their homework. Okay, so that's how we read these graphs. Let's take a look now at a few questions below. So we can answer questions like, what's the median? Well, if we know that there were 50 people or 50 data points here, then halfway to the middle, the 25th person would be the median person. We can trace that over. We can trace that down. It's not exact. It looks like it might be like 68 minutes. One thing that's important that you understand though, 25 is not the median. That's a frequency, okay? When we're talking about this, in fact, the only really thing that here is that's a variable is the amount of time. The median amount of time is 68 minutes. What else could we answer? The interquartile range. Absolutely. Okay, so if we're dealing with the interquartile range, we would need Q1 and Q3. And if this is the median right here, another way of thinking of Q1 is it's like the median of the first half of the data. So that's going to be somewhere in here around 12.5. All I'm doing is saying that's half of 25. So trace that over, trace that down. Looks like it's maybe 44. It's hard to say. So maybe that's 44 for Q1. In Q3, I'm going to find the median of the top half of the data. That's at 37.5 in terms of the count. Now, there is no 37.5th person, but this is not an exact graph either. We're just tracing over to this part of the curve. Trace it down as well as I can, and looks like maybe 84. So IQR is Q3 minus Q1. That's 40. How many data points created this graph? We already talked about that. That is 50. Here's a real-world example of a cumulative frequency graph. This comes from the Washington State Department of Health, and it's detailing through the middle of September 2020 the COVID-19 cases in the state of Washington. And they present this as a cumulative case count. And so we can see back in March, there were none. And as of this recording, we have eclipsed 80,000 cases in the state of Washington. And you can just see it grows. So like, for example, if I go to June, I want to know how many cases there had been in June. I can count up, and you see this dotted line right here is 20,000. So it's just a touch above 20,000. Notice right here, it's a little bit steeper than before and after. And same deal right here. It's a little bit steeper. When it's a little bit steeper, that means that because this is going up at a faster rate, that's a high rate of positive cases going on. So the reason I show this is something that, like, if you want to go understand the data and understand the information, in this case about the pandemic, a little bit of data literacy is required to get as much information as possible. So knowing how to read a cumulative frequency graph, you would see this, you go, oh, okay, I can understand what that means. Versus if you don't know how to read it, it's probably a really intimidating website to go look at all the data on there. They actually have a full data dashboard, which is pretty cool. But again, you do need some data literacy to understand it. Let's contrast this with cumulative relative frequency. And so this is going to be cumulative relative frequency. The reason it's cumulative is, notice on the left, well, first of all, it's labeled, of course, but it goes up to 1. And that will always be the case because a relative frequency, you can't accumulate more than 100%, or the number 1, versus what we talked about in the last two, you can accumulate as much as you want. So here's the example. Nutritionists measure the sugar content in grams for 32 drinks at Starbucks. A cumulative relative frequency graph for the data shown below. An iced coffee has 15 grams of sugar. We're going to estimate the percentile of that drink to the nearest whole percent. All right, let's find that on the graph. 15 grams of sugar. 15 grams of sugar should be right here. Go up, boink, 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 boink. Find the data point, trace it over, and it hits right at 0.2. So in my opinion, there's two reasonable answers to this. 20th percentile, 19th percentile. You might say, hey, I think it's at 20, so it's only above 19% of the other drinks. Both of those are reasonable. So why would we prefer one kind of graph over the other? Well, I think this question just showed a reason why we might prefer this graph. It's really quick and easy to read percentiles off because you just, I mean, look, as these basically are percentiles, like 0.2, 20th percentile. That was super quick. But a weakness is that I can't tell unless they told me. Now, this question they told us, but if they don't tell us, I can't just look at the graph and know what the total number of data points are, in this case, the total number of drinks. So that's a strength and a weakness of each. I also want to offer this example. I think if it didn't make sense before, this will help demonstrate how a data set turns into a cumulative frequency graph. So let's do the easy parts of this table first. If you want to pause and jot down the table, that'd be cool, and that way you'll have something to follow along with. So we have the data sort of aggregated in categories on the left. So what we're talking about is the age of our first 44 presidents at the age or at the time they were inaugurated. So we have 2 presidents that were inaugurated when they were between 40 and 44 years of age, 7 that were between 45 and 49 years of age, and so on. Let's get the cumulative frequency down first. So here we go. Cumulative frequency, so 2 9, now look at where that came from. What I'm saying is that means 9 presidents were 49 or younger. And that's what this data point is right here. It's at 9. Let's keep going. There were 13 more, so that brings us to 22. That's signifying 22 presidents were 54 or younger. And you can see that data point right there. That's 22. Let's keep going. And so add 12 more. 34, add 7 more. Add 3 more. And 44, and I'm comforted by the fact that it talked about the first 44 presidents, and I got these to add up to 44. Okay, so that is the cumulative frequency. That's where those numbers come from. Okay, so that's what's being graphed. Now, let's talk about relative frequency and cumulative relative frequency. I think I'm just going to leave the relative frequencies in fractions to make this easier. So relative frequency is 2 out of 44. Relative frequency, 7 out of 44. So all I'm doing is taking the frequency and dividing it by the total. 13 out of 44. And guys, I'm going to guess, and so on. Okay, I think you probably get the idea. Now, when I do the cumulative relative frequency, it's going to work very similarly because 2 out of the 44 presidents were 44 or younger. And now I'm going to pull the cumulative over. So now 9 out of the 44. And if you want to turn that into a percentage, you totally could. That would be fine. And then 22 out of 44, so that's half the presidents were 54 or younger at inauguration. 34 out of 44, 41 out of 44, and 44 out of 44. So this graph over here, since it's cumulative relative frequency, it's percentages, all it's doing, like for example, let's find this data point. 34 out of 44, let's get a decimal for that. That's 77.2%. So where's 77.2% on here? Boom, there it is, 60. And they have that at 59 or under, so they're graphing that right next to 60 right there. So they're graphing that top range of it, okay? Now, let's answer a few questions below. Barack Obama was 47 years old when he was inaugurated. Can we say that he was a young president? And let's estimate his percentile. Well, 47 years of age would make him fall into here. It's a little bit tricky to estimate his percentile, although what we could do is we could go on this graph. This is our best guess. We don't know exactly, but it's a good guess. We could say, all right, well, he's 47. 47's about here, so let's go up. Let's go over, and I'm going to guess he's about 10th percentile on age. Okay, Donald Trump was 70 years old at inauguration. Oh. Okay, so I'm going to say he's the highest out of 45. Only 44 out of 45 were below him. That's about 98th percentile. He's a very old president. All right, now one thing I want to make sure is clear about percentiles. Bigger is not always better. Okay, like for example, like plaque buildup in your arteries, you don't want to have a super high number for that. Your blood sugar, you don't want to have a crazy high number for blood sugar. If you're taking the SAT, you want a really high percentile. Bigger is better in that case. But I do just want to make it clear, sometimes people talk about percentiles as if it's always good to be a big number, and that's not necessarily true. If you're a golfer, you want the lowest percentile if you're doing total number of points, because the person with the lowest number of shots is the one who wins. Now on to z-scores. Z-scores are another way of describing location within a distribution. And really all it says is how many standard deviations you are away from the mean and in the direction. Okay, so that's what this says here. So let's take a quick look. If the z-score corresponding to a recent test score is 0.9, is that good or bad? That is, depends on your goals, right? But it's not bad. What that means is you are 0.9 multiplied by the standard deviation of the test above the mean. So you scored well above average in that case. If your z-score for your test is 0, that means your score is literally average. You scored right on the average. If your score is -2, you scored 2 standard deviations below the average. And that's not good. Okay, that's quite bad. You do not want that. So how do we get a z-score? Well, that's what this is showing right here. Okay, what a z-score is, you take whatever the value is. In the example from a minute ago, it would be your test score, minus the mean of that data set, divided by the standard deviation. Please make sure you had a chance to write that down. Pause the video if you need to. You definitely want to have that. And anytime I'm going too fast, pause the video and write. Okay, so give yourself time to think. Let's apply that understanding to this example. Consider the pre-calculus TLQ scores, tiny little quiz. If the mean of the scores is 2.5 and the standard deviation is 2, what is the z-score of a student who scored 8 points? Now remember, the z-score is the value, I'm going to call that x, minus the mean, x bar, over the standard deviation. So let's apply that here. So the value is 8 minus the mean of 2.5 divided by the standard deviation of 2. I'm just plugging in the values that were given. I'm going to type that in my calculator. And the z-score is 2.75. And so that indicates that by scoring an 8, they scored 2.75 standard deviations above the mean. Pretty darn good. What about a student who scored 0 points? What's their z-score? Z-score is, in this case, 0 minus the mean of 2.5. That's why it's going to be a negative z-score, by the way, divided by 2. 2.5 divided by 2. That z-score is negative 1.25. So they scored 1.25 standard deviations below the mean. Since these numbers are not opposite, that tells us that the distribution isn't completely symmetrical, right? It's because you can score way above the mean, because mean was not in the middle of the distribution, it was at 2.5, but you can only score so far below it in this case. Here's another example. In high school tennis, the average speed of a serve is about 58 miles per hour, with a standard deviation of 7 miles per hour. Gabby's z-score is 0.3. What does this tell us about her? Why don't you pause the video and try to answer that question for yourself, and try to be specific. Here's what it says. If her z-score is 0.3, and we don't know how fast she serves, but we do know the mean. I'm just using the z-score formula, by the way. And we do know the standard deviation is 7. We have a chance to calculate the speed of her serve. Let's multiply both sides by 7. And so 7 times 0.3 is 2.1. So 2.1 equals x minus 58. Go ahead and add 58 to both sides. And we get that she serves with a speed of 60.1 miles per hour. Okay, so we just knowing a z-score and a few details, we can calculate out individual values. Part B. If we knew that a player had a negative z-score for their serve, what else would we know about them? What do you think? We would know that their serve is slower than average. And if they're playing on my team, I hope that their serve has a lot of spin to it, because they're going to need something to make up for that fact. Now let's look at how transforming a data set will change a few characteristics of the data set. For this, we're going to look at the same data from before with the pre-calc data, and there they are. And let's consider the following situation. After careful consideration, Mr. Boyden, probably feeling quite bad for the scores because they weren't very good with a mean of 2.5, decides to add 2 points to each student's score. So here's the new scores. The zeros became 2s, the 8 became a 10, and all the numbers in between were all shifted up by 2. So here's the questions. How does this shift impact measures of center and of location? So we have things here like the 5-number summary. The max before was 0, now it's up to 2. Or excuse me, the min, sorry. The max was 8, now it's up to 10, so that added 2. The median, I believe, was 2 before. It also increased by 2. So the 5-number summary, so we can add 2 to each of those numbers. Same thing with the mean. If everybody's score goes up by 2, we can add 2 to the mean. What about their percentiles? If you scored a 0 and now you're at a 2, you still didn't do better than anybody else. You're still down at the 0th or the null percentile. That didn't change a thing. If you're at a 10, you were at an 8 before, you're still at the top of the class. So where you were compared to your peers hasn't changed. So the percentiles have no change. So that's different than the 5-number summary and mean. What about the measures of variability, sometimes called the measures of spread? How about the range? The range before was 8 minus 0, so it was 8. What about now? With the change, it's now 10 minus 2, and so now that is 8 still. It didn't change at all. And if you look here, the data didn't change how spread out they were. They're not more condensed or more spread out. They're just different. They all shifted together in one block. So the IQR, that also has no change. And the standard deviation also has no change. So what if I had done a different transformation? What if instead, although this is supposed to say multiply, so let's change it. What if I decided to, instead of adding 2, I decide to multiply by 2 each student's score? And so here's the new scores below. Now the zeros are still zeros, but like the 8 turned into 16. So let's look at how this changes our measures of center and of spread, our measures of center and location. The 5-number summary. Okay, the min was 0, it's still 0. The max was 16. Excuse me, the max was 8, and now it's 16. The median was 2, and now it's 4. So look at that. All those numbers were doubled. And you might say, but wait a minute, 0 wasn't doubled. Well, how would you know? I mean, 0 times 2 is still 0. Actually, it was. They are now doubled. What about the mean? Every value is twice as big, so that means the mean is also doubled. Percentile. No, that's still the same. Because remember, if you were a 1, now you turn into a 2, you're still in the same spot in line, so to speak, as you were. So no change. Now notice that's different than before. It's kind of interesting. When we're talking about the center, when we added 2, it added 2 to each of these. When we multiply, it multiplied by 2. It just directly applied. Previously, when we added, there was no change to the measures of spread or variability. What about now? Now the range is 16. It was 8 before, so it's also doubled. And the IQR is also doubled. And if you're having trouble thinking about why that is, when we multiplied by 2, look how far away the high performers are from the low performers now. The low performers were at 0 and 1, now they're at 0 and 2. The high performers were at 7 and 8, now they're at 14 and 16. They're way far away. We've actually doubled the amount of spread. So it doubles all of these, okay, all of the measures of variability. So multiplying by 2, everything except the percentile gets multiplied by that same number. Let's summarize. So here's a summary of what we just talked about. If you add or subtract a constant, then it adds or subtracts that value from the measures of center, but it does not change the measures of variability at all, because adding and subtracting doesn't affect how spread out the data are. However, when we multiply or divide by some constant, like 2 in our example, it multiplies the measures of center and location and multiplies the measures of variability, but does not change the shape of the distribution. And I don't know why it says B there. I think it means to say by A, and multiplies the measures of variability by A. So typo fixed. So that's it. That's all for today's lesson. I hope you enjoyed it, and I'll see you next time.